You wake up, coffee, alarm, the usual, but something pulls you to the window. The sky is wrong. Ribbons of green and violet are writhing above the rooftops. Not in Norway, not in Alaska. Here, São Paulo, Lagos, Bangkok, the Aurora Borealis, that thing you only ever saw in photos taken near the Arctic Circle, is dancing directly above you. It is genuinely, breathtakingly beautiful, and it means the Earth is in serious trouble. Because that light is not a gift, it is an alarm. It tells you that the particles streaming out of the sun, particles that yesterday were flung away before they could reach you, are now hitting the atmosphere directly above your head. The shield is gone. Earth's magnetic field disappeared overnight. Not weakened, not flipping, gone. To understand what that really means, you need to know what the field actually is. Deep inside the Earth, roughly 2,900 kilometers below your feet, the solid iron core is surrounded by a churning ocean of liquid iron and nickel. That liquid moves because of heat rising from the core and because the planet is spinning. That motion generates electric currents, and those currents generate a magnetic field that stretches far out into space, deflecting roughly 1 million tons of solar plasma every single day. It has been doing that continuously for billions of years. This is not a scenario about the gradual pole reversal that geologists sometimes discuss, a process that unfolds over thousands of years. This is a sudden, permanent shutdown of that liquid iron engine. The dynamo stops, the field collapses, and what happens next unfolds in stages that grow more devastating the further out you look. In the first minutes, you mostly see light. The aurora spreading across tropical skies is caused by solar particles that, without magnetic deflection, slam directly into nitrogen and oxygen molecules in the upper atmosphere. Each collision releases energy as light. From the ground, it looks like a celebration. From a physics standpoint, it is a bombardment. Within hours, the machines that hold civilization together start to falter. Satellites are the first to feel it. Solar energetic particles penetrate the electronics of every spacecraft in low Earth orbit, flipping bits in computer memory and degrading solar panels. The GPS constellation, which depends on precise signal timing from satellites, begins losing accuracy. Weather satellites develop sensor errors. Communication relays experience dropouts. None of this is instant. How fast it degrades depends on how active the sun happens to be that day. On a quiet solar day, you might have hours before serious disruptions. During a solar storm, the window is much shorter. But the real danger is not the machines. It is what the sun is quietly starting to do to the air you breathe. Within days to weeks, high-energy protons from the solar wind begin reacting with nitrogen in the stratosphere. That reaction produces nitrogen oxides, compounds that destroy ozone through a catalytic chain reaction. One nitrogen oxide molecule can break down thousands of ozone molecules before it is finally neutralized. Scientists have studied this mechanism carefully. The event called the Lasham excursion, which happened roughly 42,000 years ago, briefly dropped Earth's magnetic field to about 10% of its current strength for several thousand years. Evidence from ice cores and tree rings suggests the ozone layer thinned measurably during that period. Some researchers estimate losses of 5 to 10% in ozone concentration over years. That was with a weakened field, not a field that was gone entirely. Without any field at all, the destruction would happen faster. Exactly how fast is still a subject of scientific modeling, not settled consensus. Now here's the thing that flips your expectations. You might assume the most immediate danger is radiation coming directly from space. Cosmic rays, solar flares, something dramatic arriving from the outside. But the greater threat is what the sun does to your own sky. The ozone layer is not being destroyed by something alien. It is being destroyed by your own atmosphere, reacting to sunlight it was never designed to absorb unfiltered. The danger is homegrown. Within months to years, that degraded ozone layer allows far more ultraviolet B radiation to reach the surface. The relationship is well established. For every 1% decrease in ozone concentration, roughly 2% more UVB reaches the ground. That compounds quickly, and UVB is not evenly dangerous to all life. Some organisms are far more vulnerable than others. Phytoplankton are among the most vulnerable things on Earth. These microscopic organisms live near the surface of the ocean, where sunlight reaches, and they are responsible for producing approximately 50% of all the oxygen in Earth's atmosphere. They are also the foundation of the marine food web. Almost everything in the ocean, directly or indirectly, depends on them. Elevated UVB disrupts their photosynthesis, damages their DNA, and reduces their population. A significant collapse of phytoplankton would not just reduce oxygen production, it would begin pulling out the base of the ocean's food chain, and the collapse would cascade upward through fish populations, marine mammals, seabirds, and eventually onto land. On land, crops would show stress from elevated UV exposure, seed germination rates would decline, pollinator insects, which are already sensitive to environmental disruption, would face mounting mutation pressures. The food systems that feed 8 billion people were calibrated for a world protected by an intact ozone layer. That calibration would no longer apply. The most counterintuitive conclusion of this entire scenario is sitting right there. The largest threat to life on Earth in the early years after the field disappears would not be a catastrophic explosion or an impact or a sudden dramatic event. It would be sunlight, ordinary sunlight, slightly less filtered than before, arriving at the surface of a planet that evolved under very different conditions. But the longer you look out, the larger the threat becomes. Decades to centuries out, a second process compounds everything. Without the magnetic field deflecting the solar wind, the stream of charged particles begins stripping molecules directly from the upper atmosphere. This is called atmospheric sputtering and ion escape, and it is not hypothetical. NASA's MAVEN mission, which has been studying Mars since 2014, confirmed that the solar wind removes approximately 100 grams of Martian atmosphere every single second. Mars lost its magnetic field roughly 4 billion years ago. Today, its atmosphere has less than 1% of the density of Earth's. Earth's atmosphere is about 100 times denser than Mars's, and Earth's gravity is stronger, so the stripping process would take far longer here. Scientific estimates range from tens of thousands to hundreds of thousands of years before atmospheric erosion becomes catastrophic for life. That sounds like a reassurance. It is not, because the ozone destruction and the biological collapses would arrive far sooner than the atmosphere would thin to unbreathable levels, which raises the question that changes everything. Would humanity even survive long enough to watch the atmosphere erode? Or would the biological unraveling, the chain from phytoplankton to food systems to civilization, arrive first? And if the answer is that biology collapses in decades while the atmosphere takes millennia, then the real question is not how long the planet survives. It is how long we do. And here is where the scenario stops feeling like science fiction. The magnetic field is already weakening, right now. Over the past 200 years, it has lost approximately 10% of its total strength. There is a region in the South Atlantic called the South Atlantic Anomaly, where the field is already locally weak enough that satellites passing through it experience measurably higher rates of electronic failures. Engineers who operate spacecraft plan routes around it. This is not a theoretical concern. It is an operational reality affecting missions today. Scientists debate what this weakening means. The majority view is that it reflects natural fluctuation, possibly the early stages of a pole reversal, a process that would unfold over thousands of years and during which the field weakens but does not disappear. Life survived previous reversals. The Lashom excursion is evidence of that. A reversal, stressful as it would be for modern infrastructure, is not the same as permanent collapse, but the debate is not fully settled. And the question underneath the debate is one that the solar system has already answered. On another world, Mars had a magnetic field once, then it lost it. And Marte, sitting quietly out beyond the asteroid belt, is what Earth would eventually become. A cold, thin-aired desert bathed in unfiltered solar radiation, its oceans long since stripped away, its surface sterilized. Look back at those auroras in the tropical sky. They are still there, rippling in colors that humans were never supposed to see at these latitudes. Beautiful, undeniably beautiful. But you know now what they mean. They are not a welcome. They are a countdown. And if the field continues to weaken, the countdown may have already started. So what would the actual timeline look like if you had to plan around it? The honest answer is that no scientific model gives you a clean number. What researchers can say is that the sequence has a shape. The first casualties would be technological, arriving within hours to days. The biological pressure would build over months and years as ultraviolet radiation climbed and ozone thinned. The collapse of ocean ecosystems would follow within decades if phytoplankton populations fell sharply enough. Civilizational disruption driven by food system failures and the collapse of satellite infrastructure could compress that timeline further. The atmosphere itself, the air you are breathing right now, would persist for geological timescales. But the life depending on it might not. That distinction matters. A planet can be technically habitable and still be empty. The civilization-level consequences are harder to model, but not hard to imagine. Every major power grid on Earth is calibrated for a world with a magnetic field. The Carrington event of 1859, the largest geomagnetic storm ever recorded, induced currents powerful enough to set telegraph offices on fire and shock operators through their equipment. That happened with the field fully intact. It happened because a solar coronal mass ejection bent and compressed the magnetosphere hard enough to induce massive electrical surges at the surface. Without a magnetosphere at all, there is no bending, no compression, no mediation. The energy of the solar wind arrives directly. Events equivalent to Carrington would not be rare historical anomalies. They would be recurring conditions, happening with a frequency tied to the roughly 11-year solar cycle and the intensity of each solar maximum. Transformers that take months to manufacture and replace would fail repeatedly. Backup systems would fail. Societies that depend on continuous electrical infrastructure, which is essentially every advanced economy on Earth, would face compounding crises they were never designed to absorb. Underground living, already discussed seriously in the context of long-duration space travel, would become the most plausible short-term survival strategy. Caves, deep basements, abandoned mines, the ocean floor, places where meters of rock or water provide the shielding that the magnetic field no longer does. This is not comfortable science fiction speculation. It is the engineering logic that already governs how we design habitats for Mars. The planet without a field and the Earth without a field present similar radiation problems. The solutions would be similar too. Some researchers have proposed that a sufficiently advanced civilization might compensate using artificial magnetic shielding, large-scale electromagnetic infrastructure positioned in space to deflect solar wind away from vulnerable regions. This is genuinely speculative, not an imminent engineering option, but it exists as a theoretical concept. The energy requirements would be extraordinary. Whether the civilizations surviving a biological and infrastructural collapse would retain the capacity to build such a system is, to put it gently, uncertain. The ozone layer is the detail that keeps demanding attention the further into this you go. It is the pivot point between a difficult future and an uninhabitable one, because it determines how quickly the surface becomes lethal and how much time any adaptive strategy would actually have. If ozone depletion unfolded over centuries, humanity would have time to reorganize around it. If it unfolded over decades, the window for meaningful adaptation narrows dramatically. The rate depends on solar activity levels, on atmospheric chemistry, on factors that vary and are modeled with real uncertainty. Scientists are honest about this. The Lachamp comparison gives a lower bound estimate, but a complete field loss has no direct historical analog in the period of complex multicellular life. Extrapolating from partial evidence is the best available tool, and best available is not the same as certain. Now, for the part that genuinely reframes everything that came before, the single most surprising fact in this entire scenario is not the scale of the destruction, it is the timing. You have been thinking about a hypothetical future event, a sudden shutdown of the dynamo, something that might happen. But the field is not static. It is dynamic, and it is moving in a direction that scientists are actively measuring and actively debating. 10% weaker than 200 years ago. The South Atlantic anomaly growing. These are data points, not projections. They exist in the present tense. The anomaly is not a region scientists marked on a map as a warning for future generations. It is a region that spacecraft engineers rode around today because the electronics fail more often when satellites pass through it. The European Space Agency's SWARM mission, a constellation of satellites dedicated specifically to mapping the magnetic field, has been tracking the anomaly's expansion and drift. It is moving, it is changing. The science is live. The mainstream interpretation remains that this is a normal fluctuation in the long, complex behavior of the geodynamo, possibly the precursor signature of a pole reversal that would play out over thousands of years. Life has navigated reversals before. The fossil record does not show mass extinctions reliably correlated with known reversal events, though the Last period does overlap with the disappearance of the Neanderthals and the megafauna of Australia, a correlation that is noticed, debated, and not yet resolved. But the minority interpretation, the one that serious researchers do not dismiss even if they do not favor it, is that what we are observing could reflect something more fundamental in the behavior of the core. Not a flip, a slowdown, not a transition, a weakening trend. Nobody is claiming that is what is happening. The data do not require that conclusion, but the data do not rule it out either. And that uncertainty is the honest state of the science. Mars is the argument that demands to be heard here. It had liquid water, it had a magnetic field. The field collapsed, the atmosphere thinned, the water disappeared into space and into ice. The surface became what it is now, cold, irradiated, and silent. That sequence took hundreds of millions of years, driven by a core that gradually cooled and lost the convection that powered its dynamo. Earth's core is larger, hotter, and more geologically active. The timeline is not the same, but the physics is. The process that ended Mars is the same process that would end Earth. The question is only one of timescale, and timescales in planetary science can compress in ways that are difficult to anticipate from inside them. So go back to that window one more time. The auroras are still there, still beautiful. The greens and violets are shifting slowly across a sky that was never supposed to hold them at this latitude. Every person looking up is seeing the same thing and feeling the same pull between wonder and unease. That feeling is the correct response to the actual situation, not just the hypothetical one. Because the shield is real, the weakening is real, and the planet it is protecting has been under that shield for so long that almost nothing alive today has any evolutionary memory of what it means to lose it. Somewhere out past the asteroid belt, a cold red world knows exactly what comes next.